So hello everyone to the last extra session for this course. My name is Shamik and I'm currently a PhD scholar working uh, in the field of partial differential equations at the Department of Mathematics, IIT Delhi. So this is our extra session for this course. So what we do basically in this session, we will solve questions based on the topics we have covered in the whole course. So we'll do some questions from each of the topics and wrap up the session. So basically, just to give an overview of the whole course, so that this will help you in your final examination. Okay, so we will start without further ado. Let's start questions. So we will start with the limit cost. We initially start with the multivariate limits. So let's start with one question, and the first question will break the myth that which we have seen that the multivariate limit there is a hunch that if the numerator has a higher degree than the denominator, we expect the limit exists, but that is not generally the case for all the cases. So let me write the question first. So the question number one is it's coming from the double limits. Examine if the limit is x tending towards 0 0 exists, and the function which we have here is x cube plus y cube whole divided by x square minus y square whenever my x and y are non-zero, and 0 when my x is equal to y. So as we have seen in the limits, to evaluate the limit, first of all we get a candidate or double limit, and that how we check that the candidate or limit. We first evaluate the iterated limits. So like that's the first goal to see whether the limit exists or not. So that we will do, we will evaluate the double limit it in terms of iterated limit first to get the candidate. X cube y cube whole divided by x square minus y square. So this will be limit as x tending towards 0. This is x cube by x square only. This is 0. And if we evaluate the iterated limit on the other side, so this will be x cube plus y cube minus x square minus y square. So this will be limit as y tending towards 0. I can put x to 0. This will be just y cube minus y square. So this will be again be 0, equal to 0. So trade limits are existing, and they both are coming out to be equal to 0. In fact, much more is true here. Uh, if we take the path, if we take y equal to mx, and I have to take m is not equal to 1, then limit as x comma y tending towards 0 0 of x cube plus y cube divided by x cube minus, sorry, x square minus y square. This will be just limit x tending towards 0, x cube plus mx cube x square minus mx square. Limit as x tending towards 0, it will be x plus, it will be x plus, it will be x cube, I can take common, and so this will be 1 plus m cube whole divided by x square 1 minus m square. So as we see this, again this will equal to 0 only. So from all straight lines we are getting the value to be 0. So there's a highly chance that the limit will exist, but and also we have seen the numerator as a higher degree than the denominator. But actually in this case the limit doesn't exist, and with the myth we have that the numerator has a higher degree than the denominator, that limit will exist, is not true actually. So why is not true? I will take a specific path, and the path I'm taking is take path y equal to x into x plus 1. So this path passes from 0 0, and if I compute the value of f of x into x plus 1, sorry, f into x, so into x times x plus 1, this will be x s of cube into x times x plus 1 ka whole cube, and then whole divided by x square minus x times 1 plus x square. So once when we can evaluate this, this will be x cube, I can take common, so this is 1 plus x plus 1 whole cube whole divided by x square, I can again take common, so this is 1 minus 1 plus x square x times 1 plus 1 plus x cube divided by, this is minus 2x minus x square. If you see, I see, then this will be just nothing but x is negative of 1 plus 1 upon x cube whole divided by 2 plus x. So when I take limit x tending towards 0, f of x into x plus 1 times x, so this will be 1 plus 0 cube whole divided by 2. So this will be just nothing but value being minus 1. And this is not coming out to be equal to 0. So this is one of the paths. I am getting a value, different value. So since I'm getting different values, the limit does not exist. Hence, at 0 0, the limit of function does not exist. So how do I get this path? That's like we can do some hidden trial and eventually get this, but that actually tells that the limit is not existing, even the degree of numerator is higher. So after evaluating double limits, we started the notion of evaluating the directional derivatives, and then after that directional derivatives, we learned the notion of partial derivatives, then directional derivatives, and we see that both are not as a good candidate of generalization of a derivative in higher dimension. But we see that we will able to formulate a better definition in terms of linear transformations of a derivative, and that definition works as a good candidate to extend the definition of derivative in higher dimensions. So then we were able to define what is do we mean by differentiability for a function having more than one independent variable, and we did some questions based on that, and then after we see some that derivative can be represented in terms of a dot product of directional derivative into the vector itself if it exists. So based on that, and then we see the properties of the gradient. We have that the gradient turns out to have nice properties. So first of all, let us start with the question to evaluate the how do we calculate the differentiability function. So we have one function and we will calculate the derivative of this function, and this function is obviously having more than one independent variable. This is from the differentiability. So the question is we have to discuss the differentiability of the following function at 0 0. So the function which we have here is x raised to the power of 6 minus 2 times y raised to the power of 4 whole divided by x square plus y square, and this is when my x and y x square plus y square is non-zero. So basically at the point x are non-zero, and 0 if my x and y are both equal to 0. So again, the basic, just as we did in the evaluating the double limits, the first check we do is to evaluate the iterative limits. The same thing we do when we have to check the differentiability of a function. First of all, the first step being to check the partial derivatives of the function. So partial derivative with respect to x and y, we will see whether those exist or not. If they doesn't exist, then that will actually imply that the function is not even differentiable, because differentiability implies all the directional derivatives to exist, in particular partial derivatives with respect to x and y. So let us evaluate the partial derivatives. So the partial derivative of f respect to x is, so we have to evaluate the partial derivative limit h tending towards 0, f0 plus h minus comma 0 minus f0 0 whole divided by h. So this is limit h tending towards 0, h raised to the power of 6, and this is y is 0, so this will be 0 and h square. So this is nothing but limit h tending towards 0, h cube, and that is 0. So the partial derivative vector x is existing. Finally, let us evaluate the partial derivative with respect to y. Limit k tending towards 0, 0 comma 0 plus k minus f00 whole divided by k. So this is limit k tending towards 0. So minus twice of k raised to power 4 divided by k square minus 0 whole divided by k. And this is nothing but limit k tending towards 0 or minus 2 times k only, and this will be 0 only. So again the partial derivative with respect to y is 0 only. So the both partial derivatives exist, so we can at least have a possibility that the function is differentiable. And we also learned about the differentiability of the function, that f is differentiable at the point let's say 0 0 if and only if that this limit rho tending towards 0 of delta f minus df by rho is 0. Right, so this is the characterization which we did in our theory, and what this my gradient of f is f of k comma h minus f00, sorry it's hk. So this is so this will be just h raised to power of 6 minus 2 raised to power of k raised to power of 4 whole divided by h square plus k square, and the rho is nothing but square root of h square plus k square. So I have to check the limit rho tending towards 0, and df is also that means what df is, what is my df is fx times h plus y times k, but again both fx and fy are 0, so this will be just 0 only. This is just this is equals to limit rho tending towards 0 h6 minus 2 times k raised to power of 4 h square plus k square minus 0 whole divided by square root of h square plus k square. So we have terms like square h square plus k square sort of thing. So whenever these terms, as we have seen earlier, we just to validate this way we convert these things into a polar form. So what we do, let us convert in the polar form. So that I can take h to be r cos theta, and I will take my k to be r sin theta. So this will be equal to limit as r tending towards 0, r raised to power of 6 cos 6 theta minus 2 times cos, so k is there, so this will be twice of r raised to power of 4 cos 4 theta whole divided by, so this is h r raised to power of 3 only, 3 by 2, so it's 3 only because r is by square root of h square plus k square. So this will be limit tending toward 0 at times square cos 6 theta minus twice of, oh sorry, again this is again another typo here. This is sine 4 theta. Sine 4 theta. So this is sine 4 theta. So this thing is actually bounded in. So we have this limit to be 0 only, and since this limit is 0, the function given to us is differentiable. So that's how we used to check differentiability. So after checking the differentiability, but we learned about the gradient, the properties of the gradient, and we basically see that if you have surface, then the gradient has the property that it will fall. It will if it's non-zero, then it will be in the direction where my increase is happening to be the either the maximum or the minimum. So the maximum rate of increase or direction of increase is given by the gradient only. So based on that, we did some questions. So let's have one more question based on that, so that we have a more clarity on the property of the gradient. So question 3 is all about property of gradient. Let fxy given as half of log of x square plus y square plus tan inverse of y by x, and p, the point which I'm considering, is 1 by 3. Find the direction in which fxy is increasing the fastest at p. Find the direction of fxy in this direction. So we have to find the direction which the function is increasing the faster at this point. So we know that the thing we know is that fxy is increasing the fastest at p in the direction of the gradient. So we have to basically evaluate the gradient only. So to evaluate the gradient, what do I have to evaluate? I just have to evaluate the partial derivatives only at the particular point. So gradient of f at the point is 1, 3 whole divided by the norm of the gradient, basically to make it a unit vector, because the directions are in unit vector only. So to get the gradient, I have to calculate the partial derivative with respect to x. My function is half log x square. So this will give me half of x square x square x square plus y square, and then this 2x plus 1 upon 1 plus y by x whole square, and then this will be minus y by x. square. So this is the derivative tan inverse pi by x. So this is nothing but x minus y x square plus y square, and I have to evaluate this value at 1 comma 3. So this is minus 2 divided by 1 plus 9, so minus 2 by 10, so this is minus 1 by 5. Let's evaluate the partial derivative with respect to y. So again, when I differentiate of half of log of x square plus y square, so this will be half times x square plus y square, and this will be 2y. And when I differentiate tan inverse y by x, this will be 1 upon 1 plus y by x whole square, and this will be 1 by x only. So this is nothing but x plus y whole divided by x square plus y square only. And again, I have to evaluate this value at 1 comma 3, and that is 4 upon 1 plus 9. So 4 upon 10 is 2 by 5. Therefore, my gradient of f at 1 3 is nothing but that partial with respect to x is minus 1 by 5. So now basically I have to make it to a direction vector, so I have to divide it by the norm. So the norm of my this thing is square root of minus 1 by 5 this thing square and square of this thing. So this is 5 upon 25. This will give me 1 by root 5. Thus the direction is minus 1 by root 5, 2 by root 5. So this is our required direction in which I am getting the f to be increasing fastest at p, and that's the direction. But now so sorry, here I have to find the derivative of at this in this direction derivative. So what is the derivative in this direction? The derivative in this direction is actually nothing but in the direction minus 1 by root 5, 2 by root 5 is. So basically what is this? This is just the I have to just multiply the gradient. I have to take dot product gradient with the vector, the direction vector. So this will be basically I have to evaluate this at 0.1 comma 3. So this is nothing but my gradient is minus 1 by 5 comma 2 by 5, and I have to take multiply with this direction vector. So this is I think 1 plus 4 divided by 5 root 5, and this gives 1 by root 5. So the derivative in this direction is given by 1 by root 5. Okay. So now, okay. So let us continue. So after studying about the gradients, what we did that we use this theory of derivatives to have to get a check on basically the maxima or minima of functions of more than one variable, and we derived some test of secondary derivative test to get to get an idea that of the function we are evaluating whether that possesses a local maxima or minima. So those techniques are not always helpful because the test we saw turns out to be inconclusive. Inconclusive. So now the question after arises that what we will do when the test fails. So we have to check it manually. So let's have one question based on that way we are checking the things manually. Uh, so let us where basically the test is the secondary derivative test will fail, but we will be able to check the derivative, then check the maximum minima thing manually. Okay. So it's question number 4. We second derivative test fails. So let fx equal to x minus y whole square, find all critical points of f and categorize them according as they are either saddle points or the location of local extreme. So basically that means that this is the point of a local maxima or minima. Okay, let's first of all let me recall what the second derivative test says, and let's try to use the second derivative test. So for second derivative test, so the second derivative test, what we basically do, we try to first of all we find critical points. So critical points basically we have fx at x naught and fy at x naught comma y naught, both has to 0, and then we have this quantity d, which is fxx fyy minus xy whole square, and this is evaluated at x comma y equal to x naught comma y naught. I have this quantity So what we would like to do with this quantity, we will see that if my d is positive and fx is positive, f has local minima. Again, if d is positive and fx is negative, but this implies f has local maxima. D is less than 0. What this implies, f has a saddle point. If my d is 0, what do we have here? We have actually the test is inconclusive. So let us first find the critical points. So my fxy is x minus y whole square. So this is fx would be twice of x minus y, and fy would be twice of x minus y minus 1, right? So fx and fy equal to 0 are, it implies whenever my x is equal to y, my both partial derivatives with respect to x and y are 0. So critical points are so these are the critical points. Now let us have let us evaluate the value d, which is fx fyy minus fxy whole square. So it is my fx this is 2, fyy is, so this is nothing but minus 2 of x minus y minus 2 of minus 1, so this is 2 only, and fxy is minus 2. So my d is 2 times 2 times minus 2 whole square. So this is 0. So since d is 0, what this implies? This implies the test is inconclusive. So what do we do now? What we do, we will now have to see the manually the graph of f, and we'll see what happens at near those critical points. Okay, so to find the nature of any critical point, we will observe the graph of f near that point. So my fx is x minus y square, and then my critical points are, this is x, this is y. So this is x equal to y line. This is the line which is which is the line of critical points. Now let us see the value of my function above this line and below this line. So if x is greater than y, so x is greater than y is this region. If y is x minus y whole square. So whenever x is greater than y, this thing is actually non-zero. So this thing is a square of non-zero thing. So this is a strictly positive thing. So my function is positive in this region. And then you have to see when x is less than 7. X is less than y. So my fxy again would be x minus y squared, and this thing is non-zero, so this is again positive. So again positive. What's basically happening if I take any point x naught comma y naught, if I zoom in, so basically x naught comma x naught, because x is equal to y here. If I take any neighborhood, what I'm getting the value to be positive here as well, and on this line this is taking value 0. So if you can see that this point x naught comma x naught is a point is taking the value 0. So it is the least value we could possibly have in any neighborhood. So we see that if x naught comma x naught is 0 and this is less than equal to my fp fxy, where x and y belongs to neighborhood of x naught comma x naught. So this is my f is a point of local minima. X naught comma x naught is a point of local minima, and the same thing can be done for any x naught in the Rn. So this whole line, all sort of critical points are actually a points of local minima only, and we can see this by this analysis of seeing the function locally, and all the points are points of local extremum. So hence all the critical point are points of okay. So so whenever our second derivative test fails, what we try to do, we try to see the function manually and try to see that whether we have a point of extrema or extrema, or it's a saddle point. So lastly, let's have one question from the integration theory, which we have just studied in the last few weeks. So that integration theory, we basically we tried to an application of integration theory. What we did basically we try to find the volume of the surface is bounded by some curves and something like that. So one thing which was there is that we were able to, some integrals we are not able to directly evaluate. So for that we just need a change of transformations. So in the same basically we will see in our following question that we will be evaluating an integral which is volume of some surface, but that integral cannot be directly evaluated, but with the help of change of variables we will see that we are able to basically evaluate the volume by changing the variables. So using the given transformation, transform the given integral and evaluate them. Okay, so let me write the integral. So let me write the transformation and the integral which we like to evaluate. U equal to x, v equal to xy, w equal to 3z, and I to be square y plus 3xyz dv, where my region of integration is given by this region in R3, so yz in R3, on the x and y and z in R3 such that my x is lying between 1 and 2, my xy is lying in 2, and z is lying in 0 1. So one of the transformations we have to naturally consider is taking the variable xy to as another variable. That's the order transformation we are already taking here. So let us evaluate. So how do we evaluate the thing? Basically we have given variables in u, v, w form. So here my function is given as x square y plus 3x yz. Now since we have given the Jacobi which you have to evaluate is actually the Jacobian is given as del of x y z whole divided by del of u v w because of new variables. But since we have a u v w in already in x y z form, so it's better to evaluate the Jacobian in reverse direction. So what do I mean by that? I know that the 1 by Jacobian is del u v w whole divided by del of x y z. And I mentioned the technique to write this Jacobian. So u, v, and w, and the derivatives we have to take as x, y, and z. So I have to take the derivative of u with respect to x, y, and z. So u is x only. So when I take derivative with respect to x, it will be 1, and then it will be 0, 0. And my v is x, y. So this will be y, x, and 0. And finally z is equal to w is 3z. So this is 0, 0, 3. So when I evaluate this, this will be just 3x. And what my 3x is? 3x is 3u. Now my work x is lying between 1 and 2. X is lying between 0 and 2, and my z lying between 0 to 1. But all of this implies that u is lying between 1 and 2. My xy was v, so my v lying between 0 and 2. And finally z was equal to 3z, so my w will lie between 0 to 3. So we can now calculate the I is nothing but this integral x square y plus 3x yz dv. So this is the integral which I like to evaluate. So since I'm now calculating in terms of PUW, so we will so x square y is, so I can take x to be u and xy equal to v. So u times p and 3v since my xy is v only, and 3z was 3, so I can take z equal to w by 3 dv. And this is my region new transform region into, sorry, we have to put Jacobian as well, and Jacobian is 3u, sorry, 1 by 3u dv. This is 1 by 3, and my region this is given by u varies from 1 to 2, v is from 0 to 2, and w is from 0 to 3. and v plus w only. So it's dw, dv, and du. Sorry, it's v by u. So 1 by 3. So u from 1 to 2, v from 0 to 2. So since I'm integrating to w, this will be just nothing but 3v plus v by u. So this is w square by 2. So it will be 9 by 2 only. So when you evaluate this, so this is nothing but now I have to integrate respect to v. So this is 3 by 2 v square and this evaluated 2 and 0. This is 9 upon 2v and again v square by 2 and evaluated at 2 comma 0 du. 1 by 3 u into 2. So this will be 4 only. So it's 6 plus 9 by 2 into 4 again du. So I can take 3 common. So u1 to 2, 2 plus 3 times 2, it will be 6 by u du. So when I evaluate with respect to u, this will be 2 only, and this is d log u. Hold on, so there's one more 2 which I missed. So this is actually 3 only. And this actually gives me 2 plus 3 log 2. So this basically gives me the value of my integral after transformation. So that's how you basically use to calculate the integrals. Okay, and so with that we have covered those sections which we are used in earlier weeks, and I think with this exercise we are able to at least able to solve those we are able to now have recall the things which we had done earlier weeks and now have a better grasp at solving these. Okay, with that I'd like to end my session today. Thank you.